Section 5.5, Factoring Differences of Squares. When you have a binomial times another binomial, and the only difference between the two binomials is the sign between the first and second term, we find that when we multiply these using the FOIL method, first terms multiplied gives us x squared, outside term multiplied gives us a positive 2x, inside terms when multiplied together give us a negative 2x, which when we add those like terms together cancel out, and last terms multiplied, a negative times a positive gives us a negative 2 times 2 or 4. When we multiply binomials that are a sum and a difference of a first term and a second term, we end up losing a middle term, and we only have two terms, and we refer to these as a difference, because of the subtraction, of squares. A difference of squares can be factored as a product of two binomials. So when we were multiplying, we went this direction, and now with our factoring, we will divide this polynomial into what multiplied together to give us that polynomial in the first place. So factoring a difference of squares, such as x squared minus y squared, factors into the square root of the first term minus the square root of the second term, square root of y squared is y, times that same binomial, only with the opposite sign. And it doesn't matter if you start with a subtraction or a plus, it's just so that one has a minus and one has a plus. These are actually called conjugate pairs, and the spelling on that is C-O-N-J-U-G-A-T. So these are actually conjugates, is the fancy mathematical term for that. When you have a sum of squares, you might think that it's x plus y plus x plus y, but we saw when you had x plus y multiplied by itself or squared, it will generate a middle term. When you have a sum of squares, there is no way that you can factor this into two binomials that generate this as a result, and this is a prime polynomial. So let's take a look at factoring. Some examples here. It's two terms. The greatest common factor is 1. Can it be a difference of squares? We'll check the first term. Is it a perfect square? It is. X times x is x squared. The square root of 49 is 7. That's a difference, a subtraction. So this will factor into the product of the sum and the difference of the square root of those two terms. And you can do a quick multiplication using the FOIL method to verify that outside, inside, our middle terms cancel out, first terms gives us the x squared, and last terms gives us a negative 49. And the next one, nothing common other than 1 between the two terms. Is it a difference of squares? Well, the square root of the first term is 5x. The second term is a perfect square, with the square root being 7y, and because we have a difference, this will factor into conjugate pairs, with the square root of the first term minus the square root of the second term, same two terms, only with the opposite sign. And again, a multiplication verifies that this is an equivalent expression. In the next one, doesn't have to start with a variable. The first term can be a constant term. Is it a difference of squares? Square root of 100, since that's a perfect square, gives us 10. Square root of x squared is x. We have a difference, so we will have the product of the conjugates, 10 minus x and 10 plus x for this term. They can also present themselves as rational numbers. Here is our fraction. Same thing, nothing common between the two terms in this polynomial other than our greatest common factor of 1, which we can't do anything with it. Since it's a two term, we should check to see if it's a difference of squares. Square root of y squared is y. what times what, being the same thing, gives us 1/16 is 1/4. 1/4 times 1/4, multiply numerators, multiply denominators, gives us the 1/16. So the square root of 1/16 is 1/4. And we have a difference as well. So we will have the product of the sum and differences of our first square root and second term square root of a y minus 1/4 times a y plus 1/4. In our next example, we have two terms, nothing common other than 1. Perfect square, square root being x. The second term is a perfect square, square root is 5, but we have a plus. This is not factorable. Again, if you're thinking both signs would be the same, just to show you why this isn't the case, if you multiply your first terms together, you get an x squared. That looks good. And if you only multiplied your last terms together, that would be exactly what we have, but this is only the f and the l. We have to multiply the outside term, which gives us a 5x, and the inside term, which gives us a 5x, which will give us a 5x plus 5x, or 10x, which is not what we had. So nice idea. Try other signs. It's not going to work. When you have a sum of squares, it is irreducible or prime. In this next example, two terms, nothing common other than 1. Is it a difference of squares? What times what gives you x to the 8th is x to the 4th. Is this a perfect square? What is the square root? 4y squared times 4y squared would give us the 16, and it is a difference. So this will factor into an x to the 4th minus 4y squared, square root of the first and second terms, and again those same terms only with the opposite sign of what we started with. Whenever you have factored and you have terms that have powers higher than 1, you should be on guard for the possibility of factoring further. And if we look at this first term here, we have two terms. Could it be factored further as a difference of squares? X to the 4th, the square root is x squared. 4y squared is a perfect square because 2y times 2y gives us 4y squared, and we have a difference. This has a sum. We can't do anything further with that second binomial, but the first binomial can be replaced with the factored form of the product of the sum and difference of these two terms. So we have an x squared minus 2y and an x squared plus 2y. These two binomials would multiply to give us the x to the 4th minus 4y squared, and then we have to be sure to include that other binomial that we factored from the original, so that these three binomials multiply to give us the original one. Can we break it down further? This is a perfect square, but 2y cannot be broken down any further, so we're done factoring that problem. In this next example, we have three values here that have x's in them, but not the 4th one, so looking for a greatest common factor doesn't work. When we have a 4-term polynomial, first step would probably be what we've looked at before, grouping them, the first two terms together. What's common between the first two terms is an x squared. Dividing out an x squared leaves an x, dividing by an x squared leaves a 3. We have essentially an x and a 3, but our signs are exactly the opposite. And if you remember the trick that we had, if we factor out a -1 or divide by -1, it changes the signs. Negative over negative is positive, positive divided by negative is a negative, and now all of a sudden we have the same term on either side of that subtraction. So we'll factor out the common binomial. We can have binomials that are the greatest common factor, and this happens to be the case. When this term gets divided by x minus 3, the x minus 3 cancels out, leaving x squared. When this term gets divided by x minus 3, the x minus 3 binomial cancels out, leaving a negative 1. We can do a quick multiplication to be sure we have what we originally had, but again, anytime you have a power higher than 1, you should be investigating further for the possibility of factoring more. Nothing here, but because of a square term, I'm suspicious of this binomial. X squared, square root is x, 1 times 1 is 1, it's a perfect square, and we have a difference. This second binomial can be broken down further into conjugate pairs. So the final factored form for this would be the x minus 3, but replacing x squared minus 1 will be the square root of the first minus the square root of the second times square root of the first plus square root of the second. When you multiply these two binomials together, you should end up with an x squared minus 1. Multiply it by your x minus 3 will eventually result in those 4 terms. A couple other special versions here of difference of squares. Here we have something squared minus 49. This clearly is a square, whatever that is, regardless of its complexity, and 49 is a perfect square. Square root of a term to the second power is that term. Square root of 49 is 7, so we have a difference of squares. Difference of squares factors into the product of conjugate pairs. So we would have the square root of the first term, and I'm writing it in parentheses, minus the square root of the second term, times square root of the first term, plus square root of the second term. Now because it's just a subtraction of 7, the parentheses here have no effect, so we could eliminate those parentheses and write it as x plus y minus 7. And likewise here, this is all addition in here, so there's no concern about a subtraction of a quantity to worry about a sign. So we could express this as a trinomial times a trinomial for its factored form. We have one more example here, which has 4 terms in it. First procedure probably would be to group them 2 by 2 as we have in the past. There's a common m. Factoring out an m leaves an m plus 4. Nothing common here other than looking at these 2 terms. Square root of 4 is 2, and the square root of 9n squared is 3n, so it would be a 2 minus 3n times 2 plus 3n, but that's nothing in common with the binomial that we factored from the first 2 terms. And we could try the first and third and the second and the fourth term and different combinations, but sometimes we can group 3 terms together and look and see whether that results in anything that can be factored further. And it just has a feel that m squared plus 4m go together, and if we would group it with the 4 this time, a 3 against 1 scenario, and ignore the minus 9n squared temporarily. We just looked at perfect square trinomials, and the shortcut for that possibility is the first term a perfect square? It is. Is the third term a perfect square? It is. Is the middle term double the product of the square root of the first and the third term? And it is. So in place of this trinomial, both signs are the same, both will be positive, we will write an m plus 2 quantity squared, And we can't forget about the minus 9n squared that we ignored temporarily. This now has a look of this problem that we just had, where we have something squared minus a squared. We have a difference of squares, just a little more complicated, but square root of something squared is that binomial in this case. This is a perfect square. Square root of 9n squared is 3n, and we have a difference. So this will factor into the square root of the first term minus the square root of the second term times square root of the first term plus square root of the second term. And just like the last example, there is no subtraction of a quantity, just a subtraction of a term. The parentheses are having no effect, so we could have written it as the following. Here we can kind of see that conjugate pair and where it came from. But if we had to type this in or enter our answer again, we could express it as a trinomial times a trinomial. And multiplying that should verify that we have an equivalent expression to the original 4-term polynomial where it started from.